I am Aditi Pandit, and I'm a principal engineer at Ahana. And I'm going to talk today about building large-scale query operators for Prestissimo. So the Prestissimo project is the project for the C++ Presto worker engine. And it's a joint collaboration between Meta, Ahana, ByteDance, and Intel. So we are the most active participants. So the talk outline, I will first present about the project Prestissimo and Velox and the motivation for these projects. There have been previous talks about Velox, and they're mostly about the library and also about how Velox is used internally in data engines at Meta. My talk is going to be focused on the query processing workflow. So we're going to start with a SQL query. It's going to be submitted to the Presto cluster, and then we see like how it's transformed further. So the bulk of this year, I mean, I've been working on this window functionality, and I will use that as the central part of the SQL query that we're going to look at. And it's going to tie into like all the Velox framework components that were used to build this operator. And Velox has much more, but this talk is going to touch on vectors, buffer pool, HashTable, full to disk. So each of these components is their own specialized area and goes into like many details into the system and how to use it most efficiently. Where I come in is the actual query processing and how it kind of put all this together to achieve the objectives. And we think we have something novel, so let's see how this goes. So Project Prestissimo, so this is this new initiative for the C++ Presto worker. What we build here is like the Presto worker executable, and it's going to be a drop-in replacement for the Presto Java worker today. And it composes of two parts. So you have the Prestissimo server part, and there's Velox. The Prestissimo server part is pretty much like an implementation of Presto's HTTP interface, and it's all the server orchestration. So basically, the three main things are that plan fragments are submitted to the worker engine, and this is sent from the coordinator to the worker, and the worker will execute this plan fragment and splits. Prestissimo also includes the interpretation of the worker-to-worker exchange wire protocol. So basically, we pick up the data buffers that are sent by the coordinator or by other workers, and we have all the like serialization, deserialization, implementation of the protocols to interpret those data buffers into Velox vectors, and this is again like super efficient. And the last thing that's in the Prestissimo server is like the status reporting. So your coordinator can ask for task updates, and the Prestissimo server reports all stats back to the coordinator. So this gives a better like visualization of what's happening in the system. The Presto coordinator is the same, so the parser, optimizer, scheduler, everything is the same. The Hive meta store is the same. And the server orchestration comprises of like sending requests to the workers to execute plan fragments. You have serialized pages flowing everywhere, and the coordinator can ask the workers for task updates. The part that we are changing is each green box, which is like the server that's executed at the work earlier. So that's a Prestissimo server, and it will. So it is the same implementation of all the HTTP like interfaces that were in the previous slide. And so that's the server orchestration part, and basically it builds the data structures that conform to this Velox API, and we hand it over to the Velox library for doing all the data processing. So we have the Velox drivers is one part of the system, and there's a Velox Hive connector. So this is the system diagram. So what are the benefits of Prestissimo and Velox? So yeah, the huge performance boost. Velox is very heavily vectorized, a lot of very heavy adaptive runtime optimizations, and I'll kind of give examples of this further down. And so, of course, like we go very far to get the best performance numbers. We have a lot. I mean, we exploit all the like instruction pipelining that the CPU can give to the greatest degree. There is no Java, it's all C++, so no performance cliffs, no Java processes, no JVM, no garbage collection. All the memory management and SIMD are explicitly controlled by this library. And so there's no performance cliff, and the other thing also applies that we can better understand what we've built because we have so much control over it. And so Velox takes this idea a bit further along because it's a library of all these data processing primitives, and it's used across data engines. So like the Prestissimo is the Presto worker engine, and many of these Velox data processing components are also used by Spark, and that's part of all the Sapphire and all these other things. So this is all, we hope it'll be easier to build and operate at scale. Okay, so going with like the query example, right? So let's start, the bulk of this talk is going to be about the query processing. So this is the query, that is the motivation. So it's a window query, and what we're doing here is that we'll scan the orders table. Orders is a table which has the order ID, order date, clerk who executed the order, price of the order, and what we want to compute is the rank, and it's a ranking function, so we're going to partition the data by each clerk, order the rows by the total price, and then compute a rank value which kind of tells you which is the highest, I mean going from 1 to as many rows, which were like the ranking of like the most prized order. And then all this, the output of this is going to be ordered at a global level by clerk and rank, and you see that's the final result. So yeah, so logically you have a scan project, PlanNode, feeding into a window, which is going to do rank over partition by clerk, order by total price, and then there's a final sort by clerk and rank. So logically that's what we want to do. So this slide kind of demonstrates a bit deeper and kind of goes, explains the window processing in, visually. So you have the input table, and you partition it. So in this case, you're partitioning by ID. So you have, your data is split by partition by the ID column into 2 partitions. Then we look at each partition individually, order by the date column. And so my previous example was ranking, which is a relatively simple like window function. The window function, like the window spec, in addition to the partition by column and order by column, also can include a window frame. And so window frame is something like rows between unbounded preceding and current row, which says that, okay, this is the entire frame over which you have to compute your window function. And I mean, this could be growing, this could be moving, and this could be all random too. So in this example, right, we are computing the average between like one preceding current row, so between the 2 rows. And so this is the typical usage that we see. So this is moving like averages. So every aggregate function can be used as a window, and this is the typical usage of it. And the TP-CDS queries all use like aggregates as windows, and that's what everyone is optimizing these days. So, going over the like high-level algorithm of the window operator, you partition your input data by partition keys, sort each partition in the spec of the order by keys, and then compute the window function. So each row also has a frame context. You like take your partition, figure out what are the frame boundaries for each row at a time, and then give this over to the window function, and the window function goes ahead and computes it. The 3 categories of window functions supported by Presto are ranking functions. So you have rank and percent rank and dense rank and others. And there's also a class of value functions. So value functions let you access any like row in the frame depending on some specifics. So you have like first value, last value, nth value, and then is the aggregation. So pretty much every aggregate in Presto, every aggregation function in Presto can be used in a window function mode. So as would be expected, we took that SQL query and got the query plan. So this is all that the coordinator did. And I mean, this is kind of expected. So the logical plan translated into 3 fragments. At the lowest fragment, fragment 3, is the table scan. And that scans the orders table. We've also like hash partitioned it by clerk, which was the partitioning column. It fed into the middle fragment, which actually does the window operation. And the window operation, like, further looks at each partition and orders it and does the window function computation. And here you can see that my example had rank over range unbounded preceding current row. And this fed into the next fragment, which is going to do like the global sort. And this will be output. So this is what the server like execution plan kind of comes off. And so each fragment is the part that's going to be executed by the worker. So we're going to focus on the second fragment because that's where the window operator is. And so the server gets a request for executing the fragment. If it is like a table scan, it also gets splits, which tell it which part of the table to read. And so every worker just sees this fragment. It knows, so it gets data through like the remote sources here, and yeah, so and then the output data is passed on to the next worker or the coordinator. So in the previous example, right, in this we care about fragment 2, which has the window operator, and so in the Presto like world, you get a fragment plan comprised of JSON nodes, which are like Presto PlanNodes. And what we do is, so in the Velox world, right, the Velox API comprises of these Velox PlanNodes, which are like kind of almost equivalent to the Presto PlanNodes. And there's also a list of, so each plan node, well, almost each plan node has a corresponding operator node. And the operator is like the workhorse of the Presto server engine that does all the data manipulation and everything. So for the purposes of this example, so these are all the nodes that are supported in the library today and the operators. So for the purposes of this example, we care about table scan, order by, and window node, and the corresponding operators for that, again, table scan, order by, and the window operator. So the window operator is what we have newly written. So yeah, like most of these correspondences are one-to-one, but sometimes they can be, you know, certain plan nodes can be combined and done by a single operator. So like usually, right, you combine filter and project and you have filter project operator. So sometimes one node goes into multiple, so like a hash join becomes a hash probe and a hash build operator. So it's not exactly 1:1, but your Presto server engine first like builds the Velox plan nodes, and it invokes a Velox API that kind of builds these operator pipelines. So this visually describes what actually happens. So like in the previous example, right, your query plan had all these stages, and these stages kind of, the scheduler figures out that, okay, we want to do so many tasks for each stage, and each task is what is handled by a worker. And if I kind of blow down into that task, and especially the one that we're interested for the fragment, right, your task itself has all these nodes and operators, and there is another level of partitioning because like you can run each operator in a pipeline. And so there's another level of parallelism where all these like, that's what's happening in the process. So like these are all the operator pipelines that are running. So in my example, you have a remote source node which is kind of picking data from the lower level scan project. And there is a partitioning like exchanges like kind of show that like this can blow up into multiple pipelines. So that local exchange is like it's aware of partitioning key, and it kind of blows into 3 different pipelines, and then in each pipeline you're executing a window operator. So each window operator here will see a portion of your input rows and process it and put it in this partition output, and the partitioned output will like push the buffers into like the next stage. So that's what's happening in the server process. And now we go another level deeper into this driver loop. So you saw like, so driver is a single thread of execution of an operator pipeline. And this is the Presto design. I mean, so the Velox design sort of follows the Presto design. And what we're trying to do is like get data from the closest downstream operator that can generate data, and it's available for output. So in this example, you had operator 1 feeding into operator 2 into feeding into operator 3. So the data is actually going like from bottom to top. But you are actually querying each operator for the output rows from top to down. And so you get like the topmost operator that has data to give you, and that if it has data to give you, you send those output rows downstream. And so like in this case, operator 3 kind of goes into, it's into the network, but operator 2, like if operator 3 didn't have rows to process, the driver queries operator 2 for output rows, and if it has output rows, it'll generate them and feed it into operator 3. So this is like the, this is how execution is proceeding inside the Velox driver loop. And the window operator is a particular operator. So it's an operator in this component diagram. And so again, this is a bit simplistic because Velox has more stuff. So you can basically, if you're blocked, you can say that the operator is blocked, and then the driver can take that off the CPU thread executor and start giving threads to other operators that can proceed. So then drilling down one more level into the window operator. So you have to, we end up implementing these 3 calls, which is like add input, no more input, and get output. So add input is what is used to actually pump data into the window operator. And so for the window operator, you need to see all the input rows before you can do anything. And so what add input does is it takes all the input rows, stores it into like a row container, HashTable, and this could spill to disk. And so once you see all your input, the driver framework invokes this no more input function. And like once you get this no more input function call, you kind of know that all your data is seen, and you can start outputting rows from the operator. So what happens now is that you prepare your partitions and sort the partition data by the sort keys, and that's going to build a stream for each window partition on which you're going to like basically call the window function, and and the output row generated will be actually pushed to the output. So okay, so in order to prepare partitions and order them by with the order column needed, there are multiple things you could do, right? So, but the easiest thing to do is to use a sort-based algorithm where you can sort your row container by partition by keys followed by order by keys. And with this sequence of ordering, the final sort gives you like your entire data stream ordered in the order in which you can process, in which the operator can process the stream to generate window function output. And another way to do this is to use a hash table. So you can hash by your partition key, and your hash table will split your input data into like hash partitions, and then you can operate on each partition at a time, sort all the rows in the partition, and that will cluster your rows in the right partitioning and order by expectation of the operator. And then you invoke the window function on the data stream that you see. And in order to invoke the window function, like we said, so this is vectorized, so it goes block at a time. And so for you, we are kind of operating with, at the level of block data. So you have a whole bunch of like rows that you're going to work on. And so you prepare this set of output rows to be processed by the window function. And what that means is for every row, you figure out what are the pairs and what are the frame boundaries for the rows for each row. And then this whole metadata, so to speak, of the row, the pair, the frame, is passed to the window function, and the window function computes the window function value. And and this is all like a block at a time, or vector at a time. So what are the complexities in all this? I mean, this sounds complex, and there's even more complexities. So yeah, so the window operator needs to see all the input data before it can return any output, Velox provides these structures called row container or hash table to actually store the data that it sees in the operator. This data may not fit in memory, that's obvious, so you need to spill to disk. And yeah, so you spill to disk, so maybe you figure out which partitions need to be spilled to disk, and you spill them to disk. And furthermore, right, this input data may be heavily skewed, so it's possible that even though you partition your data, your partition was also huge, and a single partition also didn't fit in memory. So we do some tricks like sorted spills so that we can like stream partitions back into like memory when trying to like do the window function computation. But that also might not be enough because your window is going to operate over a frame of rows, and what if that frame of rows also didn't fit in memory? So there is like multiple layers of things not fitting into memory. And then let's go into the function computation. So the rank function that we saw was among the easier ones because it relies only on ordering. There's no frames. You only see the prior row. Value functions randomly access rows in the frame, and the aggregates compute over the entire frame. So if you're looking at a computation for an aggregate that's like order n, this could blow up into order n squared. And so you have to do some smarts there to ensure that your aggregation processing is not repeating computations. So there's some stuff there. And also, like, you could be maintaining expensive state, and I mean, if this expensive state gets too big, then that also needs to be split to disk. So yeah, that's it in a nutshell. Okay, so I've given this as an example of the window function API to demonstrate that, you know, we're kind of working on vectors and buffers because this is like a vectorized engine. And the window function, like, this is similar to other like data engines. You kind of create a window function object, and then you know, as the partitioning and window function operator, the window operator is executing, right? For as you see each partition at a time, you call reset partition to tell the function that, okay, now you're going to see a new partition of data, and then you keep calling apply for all the output rows that you're going to generate. So you go like one block at a time and keep calling apply for each set of rows that you can output to the next operator. And so, like, the interesting structures are in bold here. So you have a window function, which is just an instance of this class. But like, you have memory pool in here. There's hash string allocator. There's type pointer. There's vector pointer. There's buffer pointer. So yeah, this is all stuff from the Velox framework. So let's drill into this. So the Velox framework is vector-based, and what this means is everything is on this vector pointer thing. So you have a vector of results that you're going to populate. And every vector, right, it can be like, so we have all these like different kinds of vectors because we want to optimize processing. So based on different encodings, you have constant vectors, flat vectors, dictionary vectors, run-length vectors, bias vectors, and you know, the operator tries to be the most efficient. So we like, you cannot assume what kind of vector is your input. And so like the processing in each operator is complex, but then that's what we have to do for the performance we want. And each vector is basically, you can think about it as you know, a row of types, and we have implemented all the common types that are in Presto. And so yeah, function and operator logic happens in very tight loops, exploits all the CPU instruction pipelining you can get. Now these vectors are allocated from memory pools. Now memory pools, so Velox has a whole lot of memory pools, and these are like hierarchical. So you have your operator memory pool, and all the operator memory pools are chained. You have a task memory pool that kind of comprises all the operator memory pools. And so we maintain count of how much memory is allocated and who's using what. And all the buffers, so basically a vector it maps to a memory buffer, and the buffer is a contiguous piece of memory. The buffers are reference counted, so basically they can be reused between vectors, and these vectors can be reused across operators. So basically, if your operator doesn't change anything, you can just simply pass that buffer of vectors to the next one. And there is a lot of optimizations for zero copies in between. And so like, this is kind of exploiting all the memory locality you can get to. And so like, we can really do like good SIMD, use SIMD as much as we can. And behind this buffer pool, the buffer pool memory management is inspired by this Umbra paper, which is the evolution of Hyper, which is a system that's being built at TUM. This is the latest and greatest. And what this gives is that, I mean, like most traditional database systems or data engines kind of worked with a fixed buffer size. And this makes the operator very complicated because, what if your rows didn't fit into like this buffer, and then you have to like have large objects that have to be split across buffers. So what this gives you is a variable size page buffer manager. You can just ask for how much ever like size you want. And this system is designed so that the performance is very comparable to an in-memory entirely like in-memory buffer manager if everything fits in memory, and this degrades, scales and degrades gracefully beyond that. Yeah, this is very complex and not my thing, but yeah. And so to give an example of adaptive runtime optimizations, I wanted to like talk a bit about the hash table. So the hash table, right? So abstractly, you can think about it as two high-level steps. You take your keys and compute a hash value, and this hash value will then map to some memory address in the space of a row container. And where the adaptivity comes in is in this key computation. So what Velox gives you is something called a vector hasher. So you give it a vector, and it'll compute the hash values of all the columns in that vector. And this building of hash values is adaptive. So if you have very little data and like it kind of has some good behavior of like, you can use radix sort kind of thing to actually just map your column value into like array index, then, and if you are like below 2 million entries, it works in array mode, and that gives you a very easy hash function. And then if you have more than 2 million entries, you kind of go into this, if you can, you use this normalized key approach, where if your keys are like, integer types, I think Boolean, these supported types can be mapped to a normalized in64 value, and you can use that to go into your address space. But this might not work like if you have character data. And if you can't do this, then you go to the next level where you use a hash function, and we have using something from the Folly library, and Folly is like Facebook's kind of evolution of Boost. Yeah, and so this is what I wanted to, so I wanted to illustrate like what we mean by runtime optimization. So this is the kind of thing that goes on. And so yeah, so you do all this hashing, and it maps to some address of a row container, and this row container can be split to disk. So the next Velox framework component that I want to talk about is the spill to disk. Now the spill to disk operates on a row container, and if you have your hash table backing this row container, then you have partitions that are also part of all this. And so what if your partition didn't fit in memory? Or what if your entire data like didn't fit in memory? So you have this option to, with some heuristics, to figure out which partition you want to spill to disk. So an example of the heuristic that kind of comes into play is that if you have had a prior partition that's spilled to disk, maybe you spill that partition again. And when you spill to disk, we use this fancy sorted spill. So we sort the data by a combination of the partition key followed by the order key, because if we read it back in that order, we will get the stream in the order in which we want to like execute the window function on that stream and send it to the output. So we do this sorted spill thing, and what you get is a list of spill files, and Velox has this file system interface, and you kind of write these spill files to that. You give it to the file system interface that figures out where to put it on disk. And so this is what happens when you do add input and you have all this data that doesn't fit in memory. But when you want to get output, you do a merging operation, and so Velox has this like tree of losers algorithm, and it kind of looks at all spill files of a partition, and you can like do a merge sort, and that gives you the partition in the order needed for the window function computation. So that's what spill to disk looks at a high level. Now, like I explained, right, for window operator, this was just at one level where your entire data didn't fit into disk. This can go further where your entire partition didn't fit in, where even a single partition didn't fit into disk. And so, but like because we did this like merge, this sorted spill and merge, you at least got your output rows in the order that you want to compute on. But then you give this computation if you are doing an aggregate and it has some expensive state, that could also spill to disk. So, you know, we kind of can put one spill, we can separate the two spills and like kind of intelligently operate. So yeah, so we've brainstormed this a lot and kind of have come up with something where we want to go as far as possible and kind of do all the corner cases and in a degenerate mode that kind of will take us very far. So yeah, so that's all the Velox components in picture. And yeah, so we believe we have something novel. Where the implementation is right now is we've done an in-memory implementation for many of the different classes of the window function. And we're kind of working with performance tuning and spill to disk. So yeah, so I want to give a shout out to the Velox team at Meta. This wouldn't be possible without their support. And especially Marsha and Ori. Ori is like the main architect of Velox, and Pedro and Meng Shao. So yeah, if your head is spinning, it's okay.
Oh, it's on. Do you have any performance numbers where you compare existing Presto Java workers with the Presto Velox workers?
Yeah, we're doing that right now, so we will have something shortly. I don't have a number right away.
Okay.
I guess I'll ask a fairly simple question. How does the existing connector ecosystem integrate with Prestissimo? So you have to get the data in somehow.
Yeah. So yeah, that's interesting. Like, I guess like different people are going with different approaches, right? In some clusters, like I guess Meta will look at the query and figure out if it can be done entirely in C++, or like maybe you need to use a Java cluster. So some folks are like demarcating at that level.
You like that both Presto and Prestissimo work?
Yeah.
Half of them are loaders and half of them are
Yeah. So some are going with that architecture, and yeah, like Ahana might have some different ideas. Like, let's see. We're kind of like exploring all this. Yeah.
C++ connector interface that you can
Yeah, so at a high level, we have the Hive connector, and so there is an interface. It's fairly low level right now. Like you can write a TBC. There's a TBCH connector too, but yeah, either you can write a connector. Yeah, we haven't done a very great job of like exposing the APIs, but yeah, that's where it is.
So I saw on your spill to disk, I mean, you're going directly to a file system, the Velox file system interface or something. I was just wondering, have you thought about having that be more abstract? So that it could just go to some spill to whatever. I mean, it might be CXL memory on other machines. It might be spilling to a cache system. I guess I'm sort of surprised it's kind of like.
Yeah, so that's Velox file system, but that could be backed by any storage. Like, so at our level, it's just very abstract. You write a buffer. And yeah, like there is, yeah, so Velox by itself has like a async data cache, so that's where it could be going. But I mean, we will have like a cache system, like, yeah, there might be many options to explore. Yeah.
If I may go a second time, it's the assumption that a planned fragment that comes to a Presto worker, either all of the operations in that fragment are being executed by Velox, or initially can you do some in Java and some in Velox?
That is also a very interesting question. And yeah, you will hear more subsequently. I don't want to go there.
Okay.
So are there any planning side changes because of these new operators, or do you expect more information which could be used by the operators?
Yeah, right now there are no planning changes, but if we come up with like new operators and we need to make planning changes, I mean that would be a different project. Yeah, this was just execution.
So on that planning operator slide that you had talked about, like, was it table scan, order by, and window node. Is that only for, was that just specific for this example, or is that what the windowing operator, those are the, like, kind of the three operators that it's concerned with?
No, this is the list of all the PlanNodes that are in the Velox framework, and so
Yes.
depending on the fragment, like it'll be some combination of these things.
Yeah, no, I guess my question was more around, so table scan is generally the feed node for,
Yeah,
the,
yeah.
for the window
Yeah.
function, but it could have been a group by, right? Could feed into a window function as well.
Yeah. So in that case, right, you would have your table scan, and then you would have a hash ag, right? So is there aggregation node, and then that would feed into the window node, and then that would go subsequently. So then your aggregation node could translate into a hash aggregation or stream aggregation operator, depending on like. So yeah, this is the latest and greatest.